So now Matteo De Felice is working at JRC in which JRC
in the Netherlands? Yeah.
Yes, and yes. So you will. So it's also an hydro presentation,
Yeah.
but from SM that way.
Yes,
and
exactly. Well,
a different way of having hydro presented.
Good morning, everyone. So, as Roberta said, I recently joined the JRC in the Netherlands. It's the Knowledge for the Energy Union unit. And I'm taking this occasion not only to give you some details on how in the Copernicus project in the ESM we worked on producing hydropower modeling data, but also I want to give you a quick glance on how this activity can merge, can be used to do further research in the context of the project at the JRC we are working on. So in any case, I'll give you, of course, some technical details, but feel free later in this afternoon to ask me whatever you're interested on about the methodologies and the data. Okay, so the first question is why modeling hydropower? Okay, probably most of you already know the answer, but just 3 quick points. Of course, today is the most important and the largest renewable energy electricity source in Europe, but worldwide. It has some important storage. It's important because it allows to store energy in an efficient way. And also, that's the most important thing, it provides a flexible supply. So it's easier to integrate further variable generation into the system thanks to hydropower. So the idea in this figure was just to provide you a qualitative view that I apologize that probably it's hard to see the picture, but in any case, in the red line is the consumption. This is a case study, an example shown in this paper recently published. And we can see that once the wind generation goes down, that is the green, is the light green in the top, then hydro comes into to supply what is missing, this gap in the electricity demand. So this is the traditional example on why hydropower is so important for the power system and for the low carbon energy scenarios. Well, this is my personal summary, so I apologize if I missed something, but looking at the past Copernicus SIS, you can see that most of them, 4 out of 7, in some sense are really linked to water resources and hydropower. So I think this is an important signal that it's something we really want to analyze. It's something that is probably really missing, was missing at the beginning of the Copernicus Climate Change Initiative. And I had the occasion to work on the ESM project. The goal of the project, okay, I won't introduce you again this project, but in any case was to produce national time series on demand generation. This is a very important point because we had to use different approaches. If you have seen the presentation by Laurent Debout, you have seen something different from this one, because of course, electricity demand, wind power generation, solar power generation, hydropower generation cannot be managed in the same way. Hydropower especially was particularly challenging, and we opted for a data-driven machine learning-based modeling. So we found the possibility to link the relationship between the meteorological variables, like precipitation, snow depth, and the hydropower generation, because obviously we didn't have, and we still don't have a site-specific, or in any case, hydropower generation information at sub-national level, at least not for the entire Europe. So the idea was actually for us to provide those time series at a historical seasonal forecasting climate change projection timescale. This is that's why we had to make a choice. So probably most of you are already aware of this distinction between white box and black box modeling, but the point is that we are really used, maybe not me, but the physicists are really used to do some kind of white box modeling. So really know the physical process, and you try to model it through the equation. So try to really reproduce the physical system. Unfortunately, this is not happening very often, especially in the energy sector. So the other possibility is to do in the opposite side, in the black box. So you assume that you don't know anything about the system. You just you look at the inputs, you look at the outputs, and try to figure out what's happening in between. Normally, in the reality, we are always in the between. So we define it as a gray box modeling. But this is an important difference between the hydropower we had here, for example, the wind power generation modeling we done in SM. This is the main picture, of course. This is okay. The top two are the inputs we have used. All the data, meteorological data from the area interior analysis. We have used temperature, we have used snow depth, and we used precipitation. We've done a kind of processing. I don't give you so much details about that, but probably free to ask me in the afternoon. But in any sense, those was the three predictors. And then the generation was the data provided by the INSOI transparency platform that is divided in run-of-river and reservoir generation. Of course, we didn't work on pumped storage because that's a totally another story. What's in between? It's a well-known machine learning methodology called random forest. It's in simple words, it's just an ensemble of different regression trees in some way are made orthogonal in some sense that is very effective and well-known today. And in the end, we were able to model this connection between the meteorological predictors and the hydropower generation in surprisingly, I would say, way. On the left, look at the numbers. That's the correlation coefficient computed in auto-sample. So it's a kind of cross-validation. On the top is run-of-river. On the bottom is reservoir storage, hydropower generation. And there are the different countries. Of course, we focused only on the countries that have some meaningful installed capacity. Well, there is no, so that was the results. Well, we were surprised but we expected to have better results for run-of-river because you can imagine that the link between the meteorological predictor and the generation is more instantaneous. While for the storage, there are something that we are not modeling, so the operations in the storages. So, but in any case, for some countries, in the end we had good results, but anyway, we would need further investigation on this point. And this is just an example. I've chosen two of the best results. On the top is a run-of-river for France. So this year are the year, of course, compared with the one of the two lines is the INSOI data from the INSOI transparency platform. The other one is the one provided by Random Forest in cross-validation. So you can see that there is a very good overlap. In fact, France is something like 0.97 a correlation coefficient. And the bottom is the Spain for reservoir storage generation. Also here, the results are quite good. In fact, it's the correlation coefficient at 0.83. With this method, we were able to reproduce some kind of artificial time series for all this period of era interim. So in this case, we have time series, so hydropower generation since 1979 up to today, following this methodology. So, well, this what we have done, but I want to spend a few minutes on what we still can do, obviously focus on what I started to do now, but I think there are some big challenges that we'll face altogether as a community working on this sector. The first, one of the sections, obviously, some users ask us to go down, so to go to regional site level, so they want to know something very specific for a specific catchment, for a specific hydropower plant. Can we apply the same methodology I've presented here? maybe. I mean, I'll show you why I'm not sure about that. So, in case we have the data, this is, for example, is just an example I've done for this presentation. I've taken the data from a hydropower plant in Romania. It's a 8 megawatt, it's a small one. I had 11 years of data. I used the same predictors, precipitation, snow, and temperature, and I got this kind of results. Of course, this is just an example. I mean, I got 11 years of data. So, well, of course, I'm not proving anything with this picture, but I just want to give you that, yes, maybe we can go ahead with this methodology going to site level, but what are we missing? Okay, we are saying this again and again for the entire duration of the Copernicus projects. Data, well, this is a kind of doodle from the kickoff meeting of the Asian project, was data is king, yes. As you saw, I present a data-driven methodology. This means that data is the real king here. What's happening? Data can be hard to manage, and I won't spend you so many words on this, but me and Laurent, we can tell you a lot of horror stories about the data that is normally provided by different companies and institutions, but it has up some overhead and uncertainty in the data. Data can be missing or hard to find, we already know that, but also can be the case that data does not exist. Let's imagine that you use an hydropower plant recently built. Maybe not in Europe, that is not common, but it's happening now, for example, in Africa. So data is the king, but we don't have to take for granted the data richness. And also there is uncertainty, okay, maybe this is a very well-known word, but okay, we have uncertainty in methodology of data, uncertainty in measurement, observation, generation data, and also there is some uncertainty in handling the data. We are not sure of what we are looking, how the data has been produced, the kind of pre and post-processing. So we have to deal with this. So even if we have the data, it's not always simple to trust the data we are looking at. Well, some big challenges, of course, you can totally skip the figures, but I can give you one. This is one of the first challenges that come in my mind, considering the work in the European Commission. Well, we were very, of course, Europe-centric in this work, but hydropower is it's a very important source of electricity also in Africa. A lot of countries are satisfying their electricity needs with hydropower. There are a lot of new stored capacity. That figure on the left, it was a recently published paper on natural energy. Well, just the red dots were the planned hydropower dams, hydropower plants in Africa. So there is still a lot of work that is done over there. And also this paper was highlighting the vulnerability of the African power systems to patterns or rainfall variability. So it's also this another point that can be really of interest for us, that once you have a lot have countries that rely on, of course, on climate-driven generation, variable generation, it's also, they can be really vulnerable to the large patterns. So they expect, we have a lot of planned stored capacity. There will be more and more in the future, according to the program infrastructure for development of Africa. What's happening now at the Jersey? So this is a project recently started. It's a big project called WEFE. I will be involved in this work package called WEFE Energy. The idea of this project was to assess the water energy nexus in these low carbon energy scenarios, energy systems. And this is a very big project that involves a lot of different units at the Jersey. So all the units that are not they're in Italy in the Ispra Center, so people work in the renewables and the energy efficiency, and also involves two models developed in the Jersey. The least flood is a water system model, and the Dispasset is a unit commitment economic dispatching model. This is a project that will be linked to, expect to be linked with the Copernicus initiative. Why? Because, of course, there will be a lot of work on the data side here. Because for Europe, we have, of course, a lot of data. We have some official energy reference scenarios that are being produced at the JRC. And for Africa, we have data from the Energy Outlook, you know, for the IEA World Energy Outlook, BP Outlook. Also, there is some modeling work done in cooperation with the KTH and the power systems. And also some work on water will be done in-house at the JRC, and there will be data coming from companies that they acquire some commercial data sets on oil and gas fields, and also there is this big power plant database that is the JRC. So there will be a lot of data, and the results will be honestly very ambitious. So we expect to have freshwater demand at country level and also a higher resolution for the next decades for Europe and Africa, with some specific case studies. Also, to do this, it's important to try to model the entire national power systems. This is a very challenging task, but it can be done without taking the important lessons from the Copernicus project on energy that we are looking at these days. Another initiative that obviously linked, and maybe some of you are already aware of because they've been presented in some previous symposia on the C3S, was this work on the creation of HIMARS dataset. It's a dataset of time series for currently wind power generation, solar power generation. It's a hourly based, and is based on real technology mixes. And there will be lots of work on this. I will be involved in this one because now we plan to extend this also to hydropower. So we plan to produce the same time series, not only for wind and solar, but also for hydropower. And these time series are already used, and they will be used as inputs for the power system models. So that's one of the last slide. That is the idea of the next step for the HIMARS dataset. As you can see here, we expect to use data from the Copernicus data, and there will be some work with the other JRC units on the hydrological side. So this is an ongoing activity, and it will be critical to also for the power system models for the European case studies planned for this WFA project. So, conclusions. So that's why my personal opinion. Well, we are facing a complex challenges, also urgent challenges, because we need really to plan now that our future energy grids, our future society in this sense, energy. So we need also to find different solutions. So I would say that what we have done, for example, in NESHAM, and maybe this happens also for other SIS projects, where they also provide some unconventional solutions. So we never found something similar in the scientific literature. So, and we have to do that because in the end, we had to start to provide something. So, but of course, data-driven approach, they are not just the solution. There's not a silver bullet, you know. There is now today a lot of people are saying about big data, deep learning, with data you can do everything. No, not really, but we have to consider this as a possibility, especially when the other methods we have are not working or are not applicable. It's important, software and data interoperability. That's critically important because as you've seen, for the Copernicus project, but also what you're seeing for the project I want to show you for the JRC. Now we are really, all the projects are relying on different data sets coming from different sources, not only climate data sets, but also companies, commercial databases, and on-site measurements. It starts to be a limitation, a big barrier, the lack of interoperability. And finally, Copernicus today, it's it started to be really an ecosystem of different things joining together, interacting together, and it demonstrated it had to be an enabler for research-based solutions. So this is what I've really seen today. So thank you. So.